Hello, everyone. Welcome.
And to all the participants, if you haven't seen the required materials or the helpful materials, get yourself a blank piece of paper, something circular, and a Sharpie and a straight edge, if you have them available.
Okay. So these are the folks that you will be seeing more of as we go into breakout rooms. And Johnny Ashurst and I were the ones who've kind of organized this. And it's based on a workshop, a similar workshop we did in San Antonio last year and that we did last week for teachers in the country of Nepal. So Johnny and I have organized this and will be also instructors. And in addition, we have 7 other instructors, Linda Antonone from Fort Worth, Harmon Ariel from Ohio University, Mark Bell from San Antonio, Dipendra Budatoki from Ohio University, Karen Camp from Southwestern, I think that's right, Connecticut, Rachel Gorsuch from Columbus, Ohio, and Amrit Thapa from Ohio University. And we look a lot like this. Our program is going to go like this. We're going to start off with a little geometry review to kind of get you in the mood for what we're going to be working on, get some of these concepts floating around your mind. And then we're going to do a paper folding activity. As we're teaching virtually, you might think it's impossible to do hands-on activities with your kids. So we're going to try to do a hands-on activity. We'll see how that works out. And then after that hands-on paper folding, we're going to have a whole group debriefing on that breakout session topic. And then we're going to have 2 additional breakout sessions on GeoGebra. The first one is going to look at trig values associated with a point on the unit circle. And then we're going to have a discussion of sine and cosine on the unit circle. And then you'll be able to look at some other trig functions other than sine and cosine on the unit circle in the second GeoGebra breakout. And then we'll have a final wrap-up discussion. Our theme today, of course, is the connections between trig and geometry. And what we're doing today is not a brand new concept. Here's an image from the Almagest by Ptolemy that was published around 150 AD or CE. And so this is nearly 1900 years old. And this image you see here is very closely related to some of the images we will be exploring today. So we're going to be working with circles. If you just say a circle is a set of all points equidistant from a fixed point, well, that's actually a sphere, not a circle. And from the circle, we look at some the idea of a line segment connecting 2 points on a circle called a chord. And then the longest possible chord is a diameter. And to make it as long as possible, it would have to be a segment that passes through the center of the circle. Now we get to some words that you see also in trigonometry. We have a secant function and a tangent function in trigonometry. And in geometry, we have the idea of a tangent line and a secant line. A secant line essentially, I guess, would be an extension of a chord, that you take a chord, which is a segment, and you extend it out to infinity in both directions. And a tangent line osculates or kisses the circle, touches it in one point, and of course, it would be perpendicular to the associated radius. If you connected the point on the circle to the center, that would be perpendicular to the tangent line. So the tangent and the secant are going to be important for us today. And then the trig vocabulary, of course, we have the word tangent and secant show up again. The first definitions that most students in the United States encounter for the sine functions of an acute angle alpha are related to the 6 possible ratios you can have of the sides of an associated right triangle. So if you have an acute angle and you have an initial side in red and a terminal side in green, and you drop a perpendicular from the terminal side to the initial side, you create a right angle triangle. And we often talk about the adjacent leg and the opposite leg. In some other countries, they refer to the blue line as the perpendicular and the red segment as the base. But this is what you typically see, I think, maybe even in late middle school or early high school, some students first get an exposure to some of these kinds of concepts. And of course, they maybe see the Pythagorean theorem even sooner. So in the first breakout session, you will need a piece of paper. You'll need something to write on the paper. It is best if the paper is totally blank, like a sheet of paper that you get from a printer, just a white sheet of paper. And then if you have something like a compact disc or a cereal bowl or something that you can draw a circle with, and then the edge of a book or some straight object something you can draw straight lines with. You'll need those for the first activity.
Perpendicular bisector discussion on the 60.
I teach geometry, and so I'm really comfortable with what a perpendicular bisector does, the equal distance. So I get and I understand that it's an isosceles triangle.
Welcome back, everyone. We've just finished our first breakout activity, and we have been doing some paper folding. So in the chat, what do you notice mathematically, pedagogically, of how the technology was used, and think and reflect on how do you think you could use these ideas and techniques with your students. So maybe one of the things you noticed was that when you made your 16-point circle, that 12 of those 16 points, the ones that had folds parallel to the edges of the paper or parallel to the X and Y axes, where those points intersect the circle, those are the 12-hour locations on a clock. So there's an example of student work of someone who did the folding and they said, hey, these are the positions on the clock. So what kinds of other things did you notice in your groups?
So I'm asking for volunteers. Rebecca or Rob?
I had noticed that I think we were in the discussion of how do we prove that you get a 30-degree angle in that first quadrant. From the points, I was looking at if we fold, obviously the point would correspond to 1, 0 to 0, 1. You would notice the 2 points that represent 30 and 60 degrees would line up on top of each other. Therefore, showing that that's broken up into thirds. Therefore, you have 90-degree angle that's broken up into 30 degrees each.
In our group, we had some discussion about the line equal to x equal to the 1/2, and how can we construct the line of the 1 equal to 1/2 as well. We are in the middle of the discussions of the coordinates of the 45 degree. How can we get to the square root 2 over 2 and square root 2 over 2? But we do not get a conclusion yet, but we are on the middle of this kind of the discussion. So we are exploring the mathematics right there.
So if you were doing this in class, in like a standard class meeting, this might be a whole class activity, right? To get the students to do the paper folding and then to have the discussion and try to get some closure on the activity.
Karen, this is Rachel from our group. I was wondering if you would share, you were geeking out about the pedagogy and like thinking about how to implement this right away. Could you share a little bit about your thoughts?
You need to
Okay.
unmute your mic,
I did.
Karen.
Okay, so I love paper folding. I just love, constructing the square root of 2 from paper folding. I love, I just love all these ideas. So the unit circle is something I teach all the time. I do a lot of pre-calculus. I'm just doing a 3-week review for people trying to get it placed into calculus in the fall. And so this unit circle, people come with a lot of things, different things they've done in high school. And I always prove from scratch, where all these terminal points come from. But I just love the simplicity of being able to fold and know that you get 1/2 because you folded, 1 and, and 2. I just love that simplicity. And so I just feel like even though we've already covered the unit circle in this 3-week brush up, people get, they just don't feel confident with it. I want to make a video tonight on here's how you construct it yourself. Here's how through paper folding you can convince yourself that these numbers are 1/2 instead of my algebraic derivation.
Okay.
So clear immediately why you get 1/2.
And that's visual proof.
Mm-hmm. And then to get the square root of 3/2, it's x squared plus y squared equals 1. One of them is 1/2. That's an easy equation to solve.
Right. And so I going around to the different groups, like the picture that we have on the screen right now, where 8 o'clock goes across to 4 o'clock, I guess that would be y equals -1/2. And I heard people calling that a perpendicular bisector, I guess, of the segment that would go from the middle of the clock down to the 6 o'clock hour. And because that's a perpendicular bisector, you know that the location of 4 o'clock and 6 o'clock are the same distance apart as the 4 o'clock position in the center of the clock. And so you get a lot of geometry. So you get a lot of chance to review geometry, get folks talking, and the physical feel and, like you're saying, the simplicity, I think will help students see something that maybe was confusing for them in 10th grade, maybe now makes sense, and whether it's in 11th or 12th or as beginning students in college, they have a chance to revisit some ideas when they're a little bit more mature, but to do it from a kind of a straightforward way.
Greg, if I may, I had asked folks to maybe not everyone has, just in case you haven't submitted your chat, would you do that? And
right. And I'm going to keep moving because we do have another activity we want to get to. So, people were more open to sharing in the smaller groups, which is the same thing as in the class. Some of you may have seen something like this. So if you've done this paper folding, a follow-up might be with paper plates to have them create a 16-point circle with lots more information on it. And some textbooks, you see very similar kinds of diagrams in textbooks with angles in both degrees and radians and ordered pairs and all that stuff. So what we want to do now is to go to a breakout session in GeoGebra. So we've got A, B, and C, like the Pythagorean theorem, a squared plus b squared equals c squared. And so can somebody in the group tell me what I'm supposed to do? This doesn't look too interesting right now. Am I supposed to do anything?
Supposed to move point P around the circle.
Okay.
And notice what points change, what numerical values change, and which numerical values stay the same.
Okay, so I moved it to this position. The triangle looks pretty small there. I wonder if I can move off that position. Oh, yeah. I could go into the fourth quadrant. Those look like kind of round numbers there. Do we get the ones that we had a while ago on the,
You got one of them right there.
that is real close to it, right? Around 300 degrees.
Yeah.
So you get the quadrantal angles where you have these special cases and you can go into all the different quadrants.
There are infinite number of points on the unit circle, not just the 16 that we talk about all the time.
Yeah, exactly.
Oh my.
Segment A, for example, as I move my point P. And what's happening to the B value as you move through that first quadrant? Anybody want to comment on how A and B are changing?
A is gets closer to 1 as it gets closer to the x-axis.
Yeah. And what happens to B as we get closer to the x-axis?
It gets closer to 0 and
Excellent.
reversed for the y.
I think it's also important to use the language of increasing, decreasing, especially at those students who are going to be going on to calculus, to get that language in there.
Yeah.
early.
And did you guys notice that the lengths of A and B in the first quadrant are the same as the coordinates?
Are
How come A doesn't get negative?
A is a distance, so it's the length of a segment, so that's always going to be positive, even though the coordinate gets reflected into the other axis, the other quadrant.
So you were in the breakout room playing with this geometric configuration one. What interesting things did y'all notice or any kind of comments in the chat or verbal comments, oral comments?
I'll just share what Rachel pointed out at the end that I didn't notice. And she pointed it out because it annoys her, but I love it. And that is that A is always positive, but the x coordinate becomes negative when I'm on the left, and B is always positive, but the y coordinate becomes negative when I'm below. And I love that opportunity to discuss with students the difference between the length of the side and the coordinate of the point.
So the coordinates are almost like components of a vector. And that green segment, if you thought of it as a vector from the origin O to the point P, then A and B are the lengths of the sides of that vector, but the components are, I guess in this case, the 0.75 and the negative 0.66. And that looks like 3/4 and 2/3. Is 3/4 squared plus 2/3 squared equal to 1?
Yes, perfect.
Okay. So this looks almost like 3/4 and 2/3, which is a surprise to me. 3/4 squared plus 2/3 squared. Maybe it's not exactly 3/4 and exactly 2/3, but 3/4 squared would be 9/16, and the other one would
like
be.
there's some rounding here occurring.
Yeah, so there might be some rounding. But some other places you might go to something where there may be something that really is true, like maybe 3/5 squared plus 4/5 squared. Then you'd have a common denominator. Maybe that could add to 1.
Greg, we had something else really interesting that Gwyn brought up in our group.
Pray tell.
Gwyn's going to tell you.
Okay, Gwyn.
I just mentioned that there's an inverse relationship between A and B. So as A is getting larger, B is getting smaller, and vice versa.
So you've got one increasing, the other decreasing.
Yes.
So if I'm moving in the first quadrant counterclockwise, A is decreasing and B is increasing. And C stays the same. And then in the next quadrant, you can look at A and B, and then you could also look at the coordinates. And sometimes a length might be increasing, but it could be getting more negative. Like I guess in this case, the X coordinate is decreasing because the length A is increasing and is negative. So it gives you opportunities to talk about increasing in magnitude or absolute value versus increasing in numerical value, and whether it's positive or negative. So you've got a lot of you've got geometry, you've got number, and maybe some algebra. A lot of different kinds of relationships to explore.
And one more thing I want to jump in with, as you look at this positive X values and Y values in the first quadrant, and how does that relate to the second quadrant? I talk to my students about the reflection over the Y-axis. And when we reflect over the Y-axis, we're changing positive X's into negative X's. When we reflect into the fourth quadrant, we're changing positive Y's into negative Y's. And so those reflections become very powerful ways to figure out the positives and negatives of the coordinates.
Right. So if you had a live GeoGebra instead of just this app, you could take something like this and you could reflect P in the x-axis, and it would come down to a position here. And the X value would remain the same, but the Y value would be, you get the opposite Y value.
Yes.
And so you've got a geometric transformation, and you also have sort of a numerical and an algebraic transformation going on that carry with that geometric reflection. And that can be helpful when you're talking about functions, reflecting functions across axes and things like that too.
I just saw something in the chat that's a great curiosity about what is this tangent secant connection, and I'm guessing that your next breakout will help us with that.
Well, let's wait no longer. We can, let's see where we're at here. We're just looking at, when we go to the unit circle, you have this idea that the hypotenuse becomes 1, and so some of these formulas simplify. And now we're going to do another breakout. So I think we will get to tangent and secant in this other breakout, John.
Sir. You can't really see where it goes. I had it before where it disappeared. There it is.
Why is it disappearing at 90 degrees?
Because then you'll have two lines that are parallel to each other, so you cannot connect that tangent line to that secant line, or I shouldn't say secant, but to the segment OP, or OE, I should say.
Yeah, they are tangent and secant lines. Or tangent and secant segments, I guess.
Yes.
So geometrically, the intersection will go away. What about, is there another way to think about what's going on at 90 degrees other than the geometry? Can you think of it algebraically or numerically?
Well, that's when A is going to be equal to 0.
Will A be equal to 0?
A is still 1, but what's happening to C and B? Like as we go from here and start moving.
B looks like it's getting very large, potentially. And C would get large too, I guess. What's the biggest you get for B? I guess it's off the screen, you can't see it. Maybe it's like 95 units long or 1,000. I don't know.
But as we're getting to right here, what do you notice about what's going to happen to the lengths of these? Maybe
They're going to become equal.
And how long?
how long? It's a good question, Craig.
This is a TiNspire. Are you able to see it?
Yes.
Yeah.
It's the same drawing you have in GeoGebra, except I've put the triangle inside the traditional unit circle triangle, if you can follow that. So right now, for example, tangent would be the measure of this red line segment divided by this blue. Are you okay with that?
Yes.
But if we look at similar triangles, this outside triangle, vertical, over the radius of 1 is going to give us the same value.
Was it Doug Kaufman who was sharing in maybe breakout group number 1? Could you tell us a little bit about what you do?
Does everybody see definition of tan and secant?
Yes.
Okay, so what I did is I defined tangent this way. I assume the kids have the wrapping function so they can go around the circle. And I have the line x equals 1, which is tangent to the unit circle. I got the unit circle. And I say, when you wrap around the circle, draw a line through the origin and W of t here, a line, I emphasize that. And where it intersects this line here, the second coordinate is going to be the tangent. Okay, so when you start at 0, the tangent is 0, 0, because the second coordinate at that point, that's the point 1, 0. And it gets bigger and bigger and bigger. But when you're at tangent at t over pi over 2, you don't get anything. Well, you don't have to worry about dividing by 0. There's just parallel lines. Parallel lines don't intersect. So anytime your point is here or here, up top or bottom of the circle here, you don't have a tangent. It's undefined. But what I like about that is as you move around the circle, and I love color coding. So if you're in the second quadrant, you have to go backwards to hit it, and the tangent is negative, so I make it red. And you can go completely around the circle that way. The other thing I like about it is you can show that the tangent has period pi, not 2 pi, because if this is your point here and you go another pi, you get a point diagonally opposite. Well, it's the same line that goes through the origin and those 2 points. So no matter whether you're here or here, you get the same value of tangent. So hence tangent has period pi, not 2 pi. I haven't even gotten to the proof that tangent is sine over cosine, but I do that by showing the picture that Johnny showed us.
What Johnny had was something like this, but he had an active screen that looked maybe more
Right.
like this, where you can see the sine is to cosine as tangent is to 1, because they share this acute angle, the triangle O, the cosine of theta here, 0, up to the point P. That triangle and the triangle with the tangent in it are similar triangles. And by similar triangles, you have corresponding parts of similar triangles are in proportion. So sine of theta is to cosine of theta as the tangent of theta is to 1. You can see the identities of the Pythagorean identities also. I'm going to go to an active configuration here. And so like you can see that B in this picture is the tangent, C is the secant, and so 1 squared plus tangent squared is the secant squared, because a squared plus b squared is c squared by the Pythagorean theorem. And the configuration that most groups did not get to is you can actually look at the co-functions simultaneously. So you have tangent and secant. This is a reflection of the triangle that we just had across if you had an angle bisector here of theta and you reflected across that angle bisector, you would get the triangle positioned with the tangent being vertical and the secant being along a diagonal through point P. And then over here where you have the complement of theta, you have the secant and the tangent of the complement. In other words, the cosecant and cotangent. So this was the next configuration. And then this is the live configuration that shows all 6 trig functions, how they change as you move around the unit circle. So you could get, define tangent one day, define another function another day. There's plenty of material here that you could use with your classes. One of the other bonuses that you get is you get buku identities. If you look at the configurations that we discussed today, you can see the reciprocal relationships among the 6 trig functions. You can, as Doug was just saying, you can prove that tangent is sine over cosine and cotangent is cosine over sine. You get these Pythagorean identities. You also can look at what is the sine and cosine of and all the trig functions of a negative theta and see which functions are even and odd. And then the complementary functions, by subtracting from 90 degrees or pi over 2, you can get all the co-function identities. So you might spend, I don't know how many days in class discussing all the different trig identities. And this gives you a way to see the trig identities from a geometric point of view. So that's what we've got for you today. Our time has expired, and I want to thank you all for participating so completely and thoroughly. And thanks so much for being here today. Any final thoughts from the team?
This was really great, and I feel like we just scratched the surface.